You. Have fun.
Okay.
Thanks.
Hello, everyone. We are proposing to create a biocompatible septal occluder for tissue growth. My name is Rachel Arnold.
I'm Joelle Hanley.
I'm Miriam Sai.
And I'm Faith Stewart.
So the basis of our project revolves around arterial septal defects, or for short ASDs, which is one of the most common forms of congenital heart disease. It occurs when communications between atria fail to close at birth. And larger defects that fail to close at birth may require percutaneous or surgical closure to prevent complications such as stroke, pulmonary hypertension, and dysrhythmia in the future. So according to a study in 2019, approximately 2,000 babies are born each year in the US with ASD, and 25% of general population has a patent foramen ovale, also known as a PFO, which is the most common type of ASD. And the current method used to treat a PFO is a septal occluder made of either EPTFE or polyester membrane and a nitinol wiring. It's known that nitinol degrades and releases nickel particles, potentially causing nickel toxicity or allergic reactions. And the current device can also cause tissue erosion.
To approach the problem, we plan to create a biocompatible septal occluder that promotes cell and tissue growth to close the ASD. The occluder will consist of a flat dumbbell-shaped scaffold with seated cell patches on the inside of the ends. These cell patches will face and touch the walls of the septum. The occluder will be inserted through current methods with the use of a catheter and will be placed with an end on either atrial side of the ASD and part of the scaffold connecting them through the center. To fabricate the occluder, the scaffold will be made from collagen type 1 and silk fibroin. The scaffold will be dumbbell-shaped with ends being flat and twice the size of the ASD diameter, since it will not be self-centering. The cell patches will consist of myocardiocytes, hepatocyte growth factor, or HGF, and insulin-like growth factor 1, or IGF-1, to promote tissue and cell growth and increase viability and cardiac stem cell differentiation. The myocardiocytes will be derived from induced pluripotent stem cells, as they produce viable cells that are not allogenic, unlike embryonic stem cells. They'll be cultured and then seated onto the patch side of the scaffold, along with HGF and IGF-1. These images display our proposed design. The top left image shows the outward-facing side of the scaffold, while the top right displays the inside of the scaffold ends with the seated cell patch. The bottom three images display the full device from different angles.
Our septal occluder provides a biocompatible alternative to traditional occluders that use metal. The use of metals in medical devices can elicit unwanted tissue responses, such as systemic allergic reactions or tissue erosion. Tissue erosion due to septal occluders is rare, but carries a high mortality rate. It occurs because the nitinol rubs against the heart, causing holes in the tissue, which can cause excessive bleeding, and the heart can function ineffectively. When complications such as this arise, the occluder needs to be removed, but the hole still needs to be closed. Most times, open heart surgery would be required, defeating the minimally invasive device design. Our device circumvents the need for revision by incorporating materials that are biocompatible. The projected cost for the materials we've proposed is approximately $3,600. This is sufficiently less expensive than existing devices on the market, which Rachel will tell you about momentarily. If the materials are purchased in bulk, they can be stored in cryofreezers to preserve them for many uses.
Current devices on the market that our device will be competing with are the Emplacer PFO occluder and the Gore Cardioform septal occluder, which can be seen on this slide. These devices can cost upwards of $8,000, and complications can cause the cost to raise over $50,000, which is significantly more than our projected cost. The current devices also have a success rate of 95%, which means that the 5% of patients who use these devices do not have a successful experience and could include death, open heart surgery, heart failure, and many others. We believe our device will be able to surpass the abilities and advantages of current devices on the market and will be more beneficial for the patients. We found inspiration for creating this device because Joelle has a personal experience she would like to share.
Last year, I had a cryptogenic stroke and I found out that I had a PFO. I actually have the Gore Cardioform, and I've always thought about how this device is relatively new to the market, and you always see commercials about recalls of medical devices, and I would not want to personally face that challenge. researching this has definitely been really scary and eye-opening for me. Thank you. Any questions?